In this lecture, we're going to cover the normal distribution and the empirical rule. Suppose that 20,532 students took the SAT in 2020. Let X represent the score of a random student who took the SAT. What do you think the probability distribution of X would look like? Well, X, first off, is discrete. The scores on an SAT are things like 800, 850, 900. So it's discrete and countable. It's also finite. The scores are between, I think, 400 and 1600. Would the distribution be Bernoulli? Well, Bernoulli needs X to be equal to 0 and 1, only two options, and that's not happening here. Would it be binomial? Well, for X to be binomial, we would need a success-failure relationship. We would need a certain number of trials. An example of binomial would be there's 15 students, and X represents the number of students out of those 15 students who made a 1200. You either make a 1200 or you don't make a 1200, so it's not binomial. Is it uniform? Is the probability of getting a 1600 the same as getting a 1200 or getting an 800? No, it is not uniform. This is a new type of distribution. This distribution is called the normal distribution. Here is a histogram of the scores in 2020 and the frequency of those scores. We can make that into a probability distribution by taking the height of the columns, the number of people who made a certain score, and dividing by the total. There was 20,532 students. And a probability distribution can be this histogram on the right, or we can write it out, all of the probabilities in a chart. And here I'm just guessing based off the histogram here. I see that for 700, it looks very, very close to 0. So I just guess it looks like 0.002 or something like that. So a probability distribution, we can write it as this little table here, this chart, or we can represent it as the graph on the right. Both the graph and the table give us the same information. Let's talk about the shape of the bar graph to the right. First, the graph on the right is a probability distribution. That means each score, the height of the bar means the probability of getting that score. And if we add all the probabilities together, they're going to sum to 1. This is a symmetric graph. With a symmetric graph, the mean and the median and the mode are equal. If it wasn't perfectly symmetric, they would be really close to each other. But this graph looks perfectly symmetric. It also has a bell-shaped curve. A bell, like a bell you ring, it takes on that shape. Another name for the bell curve is the normal curve or the normal distribution. These all mean the same thing. The shape of a normal distribution is determined by its mean and the standard deviation. Remember, we talked about mean and standard deviation in an earlier chapter. This is the mean, the population mean, and the population standard deviation. So the mean is the center of the graph, and the standard deviation describes how things are spread out. So when we talk about a particular normal distribution, we can write it as capital N for normal, and in parentheses, mu, which is the mean, and sigma, which is the standard deviation. Now, population mean is represented by the Greek letter mu, and population standard deviation is represented by the Greek letter sigma. When we talk about sample mean, that's represented by an X with a bar on top, and a sample standard deviation is represented by the letter S. Now, because our population of interest was all SAT scores in 2020, the mean of all SAT scores is the population mean, and that's mu. And the standard deviation of all SAT scores is sigma. While if I had said, Here are 300 students who took the SAT in 2020. That would be a sample. And if I found the mean of that sample, I would use X bar. And if I found the standard deviation of that sample, I would use S. So for the graph on the right, the mean is 1150 and the standard deviation is 200. I can use a computer to help me find those values. And I can write this distribution as capital N 1150, comma 200, just like what I have highlighted in yellow. Now, many variables produce normal or approximately normal distributions. Some examples are SAT scores, heights of people, birth weight, female shoe size, and blood pressure readings. And there's many, many more variables that have normal distributions. In this section, we're going to study the properties of the normal distribution. And we're going to work with both discrete numerical variables like SAT scores and continuous numerical variables like heights of people and birth weight. What happens when we change the mean of a normal distribution, but we leave the standard deviation alone? So here is the normal distribution with the mean 1100 and the standard deviation of 200. If I change the mean, but leave the standard deviation alone, the shape of the graph won't change. It'll just be translated. It'll either move left or right because we're moving the center of the graph. So here I've moved it over 200 units. The one on the right has been moved over 200 units from the red graph. So if we think of US men's heights and US women's heights, women tend to be shorter than men on average, but the standard deviation or how things are spread away from the mean is the same or roughly the same. Now, if we leave the mean alone, but we change the standard deviation, what happens is the graphs get wider. So you can see in the blue graph and the red graph and the orange graph, they all have the same mean, so they're all centered at the same spot. But the blue graph has the smallest standard deviation. It is a very tall graph and it's a very thin graph or narrow graph. Everything is smushed together, and when everything's smushed together, all the data is close together and it's very tall. The wider the graph is, things start to spread out more. Remember that the bars all have to sum to 1. So in order to spread things out and keep everything summing up to 1, the heights of the graphs have to go down. Here are two histograms. Remember that these curves represent histograms, and the one on the left has a small standard deviation, everything's scrunched together, while the one on the right has a larger standard deviation. Here I have 3 graphs, a blue, a green, and a red graph, and let's just compare them. They all have different means. The blue graph, you look at the center of the blue graph, it has a mean of 0. The green graph has a mean of 2, and the red graph has a mean of 10. So that moves the graphs left and right. And we can see that the blue graph is the most narrow, so it has the smallest standard deviation. The green one has the one in the middle of when it comes to standard deviation. It's a little bit wider and shorter. And then the red graph has the largest standard deviation. The blue graph has a standard deviation of 1. The green graph has a standard deviation of 2. And the red graph has a standard deviation of 5. These are probability distributions, and so the mean is the expected value, and sigma is the standard deviation of the probability distribution. All normal distributions, no matter how wide or narrow, have a rule associated to it called the empirical rule. The empirical rule says that if you find the mean mu and you add and subtract one standard deviation from that mean, you will get a range of data, and 68% of the data lives within that range. Now, if you take mu and you add and subtract two standard deviations from the mean, then you will get a range of data where 95% of the data lives in that range. Here's another visual. So think of the mean is the middle number in the middle of the graph, and I calculate the standard deviation. And I'm going to take that standard deviation, add it to mu, and subtract it to mu. 68% of the time, I will have a data value that lives in that range. If I add another standard deviation and I subtract another standard deviation, 95% of the time, any data value I pick will live within that range. And then if I take mu and add 3 standard deviations and subtract 3 standard deviations, 99.7% of the time, a data value will live within that range. This will make more sense with examples. Now let's go back to that example with the SAT scores. We said that 20,532 students took the SAT. X represents the score of a random student. The mean of this graph on the right is 1150, and the standard deviation is 200. My first question is, how do we know the true population mean and population standard deviation? Is it possible to actually calculate the true mean and the true standard deviation? The answer to that is yes. There is a database with all of this information. Now, you and I may not be able to access it, but the people who run the SAT can access it, and they can give us statistics and parameters. These are parameters. 1150 is the mean, and the standard deviation is 200. Now, if we randomly select one person who took the SAT in 2020, let's estimate the probability they made 1150 or higher. Now, we're told that the mean of the graph is 1150. The mean is the median, which is the mode. In particular, it's the median, which means 50% make higher and 50% make lower. So we're just estimating here. So we're going to say about 50% scored greater than or equal to 1150. Now, if we randomly select one person who took the SAT in 2020, let's estimate the probability the person made between a 950 and a 1350. 950 and 1350, compare those scores to 1150. To get a 950, you have to subtract 200. So if we look down at the empirical rule at mu, if we subtract one standard deviation, we get 950. And if we add one standard deviation, we get 1350. So 950 and 1350 is within one standard deviation of the mean. And 68% of the time, we're within one standard deviation of the mean. So the probability is 0.68, or there's a 68% chance that the person made between a 950 and a 1350. Now, if we randomly select one person who took the SAT in 2020, let's estimate the probability they made between an 1150 and a 1550. 1150 is the mean, okay? People who made above 1150, 50% made above 1150. That's 1150 to 1600. But we don't want 1150 to 1600. We want 1150 to 1550. How many standard deviations away from the mean is 1550? If I add 200 to 1150, I get 1350. If I add 200 again, I'll get 1550. So 1150 to 1550 is from mu and adding 2 standard deviations to mu. So if we look at the graph, mu is in the center. Mu is 1150. 1350 is mu plus 1 standard deviation, and 1550 is mu plus 2 standard deviations. So we have mu and mu plus 2 standard deviations. So between mu and mu plus 2 at sigma is 0.34 and 0.135. So we just add those together. Remember, we're finding the area under the curve. This is between mu and mu plus 2 sigma. We have the numbers 0.34 and 0.135. We add them together and we get 0.475. Yogurt factory, the number of ounces that go into yogurt containers is normally distributed with a mean of 6 ounces and a standard deviation of 0.02 ounces. How does the yogurt factory know the population mean and the population standard deviation? First off, X is a variable that is continuous. We're measuring yogurt. We have to get out a scale. It's a continuous variable. We will actually never know the true mean, the true weight of the yogurt going into the containers. It's impossible for us to find that. Only God knows that amount. He's the only one who can find it. However, the yogurt company can take samples of yogurt being put into the containers and weighed, and they can make a guess as to how much yogurt is really going into that container. So in reality, we will never actually be able to find the population parameter. But right now, for what we know in this class, we're just going to assume, we're going to pretend like a little birdie told us the truth. The truth is the mean is 6 ounces. That is the population mean. Later in the semester, we'll learn how to estimate these population parameters. Now, how do you think the yogurt factory knew the data was normally distributed? Well, what it can do is it can use samples and computer modeling to determine that the data is normally distributed. So we're not going to worry about that, about how we know that it's normally distributed. If we're told it's normally distributed, then we're going to use that piece of information for us in this class. Now, do you think the shape of the distribution is going to be wide or narrow? Look at that standard deviation. It's really close to 0. I would expect to have a very tall graph and it to be very narrow. Would you want to buy yogurt from a company whose yogurt containers has a small or large standard deviation in weight? Remember that standard deviation tells us how far the data is distributed from the mean. Now you would want to buy yogurt where the weight is consistent. You wouldn't want to get a package of yogurt that sometimes weighs a lot less than 6 ounces and sometimes weighs a lot more than 6 ounces. You'd want your yogurt to be the same weight every time, be very consistent. That would mean we would want a small standard deviation weight. Let X represent the weight of the yogurt in a container. Is X a sample statistic, a population parameter, or a variable? X does not summarize the whole population or a sample. It represents one yogurt container and how much that yogurt container weighs. So X is a variable. Is X numerical or categorical? Is X discrete or continuous? The weight of the yogurt is numerical, and it's also continuous because we have to use like a scale to figure that out, and we can get decimal approximations for the weight. Now, is 6 ounces a sample statistic, a population parameter, or variable? We're told in the problem that the number of ounces that go into yogurt containers is normally distributed with a mean of 6 ounces. That is a population parameter. That's telling us about all of the yogurt. It summarizes all of the yogurt. Mu is a population parameter. It is the mean. Is 0.02 ounces a sample statistic, population parameter, or variable? It is also summarizing all the yogurt that's going into the yogurt containers. It is a population parameter. It is the standard deviation. It summarizes the whole population. Let's fill in the blanks. Using the empirical rule, about 68% of all yogurt that comes from the factory weighs between what and what ounces? So we know that the mean is 6 ounces. So in the center of the graph, you see mu, that is equal to 6. If we subtract one standard deviation, we'll get 5.98. And if we add one standard deviation, so we take 6 and add 0.02, we'll get 6.02. So between 5.98 and 6.02, 68% of all yogurt will weigh between those amounts. Now, if we take 6 and subtract 0.02 twice, we will get 5.96. If we take 6 and add 0.02 twice, we'll get 6.04. So 95% of all yogurt that comes from the factory will weigh between 5.96 and 6.04 ounces. That's a range of 2 standard deviations away from the mean. Now, one more time, we're going to subtract another standard deviation and add another standard deviation. So take 5.96 and subtract 0.02, we'll get 5.94. And if we add 0.02 to the higher one, the 6.04, we'll get 6.06. So about 99.7% of the time, all yogurt that comes from the factory, about 99.7% of the time, all yogurt that comes from the factory will weigh between 5.94 ounces and 6.06 ounces. Let's say once every 15 minutes, a container is selected from the production line and its contents are measured precisely. Let's use the empirical rule to estimate the probability that this container that we just selected weighs less than 6 ounces. Well, 6 ounces is the mean, and the mean is the median, and it's in the center of this graph here. It's to the left. Anything to the left is less than 6 ounces. 50% of the data is less than 6 ounces. So the probability X is less than 6 ounces is 0.5. If a container had just been selected from the production line, what's the probability the container weighs between 5.98 ounces and 6.04 ounces? 5.98 ounces is 1 standard deviation below the mean, and 6.04 ounces is 2 standard deviations above the mean. So we're going to look at the graph for mu minus 1 sigma and mu plus 2 sigma. And we're going to add all of the percentages in between those two numbers, and we're going to convert it to a probability, so we're going to write it as a decimal. So we're going to take 0.34 and add it to 0.34. We get 0.64, and then we have to add that 0.135, and we get 0.775. Remember, probability is a number between 0 and 1. So the probability that the container weighs between 5.98 ounces and 6.04 ounces is 0.775. You could also phrase it as there's a 77.5% chance that the container weighs between 5.98 ounces and 6.04 ounces. If a container has just been selected from the production line, what's the probability the container does not weigh between 5.98 ounces and 6.04 ounces? Now, our last example, I'm going to switch back really quick, is the probability it does weigh between these two numbers. And we're asking for the probability it does not weigh between those two numbers. So you can either look at mu minus 1 sigma and mu plus 2 sigma, add everything below mu minus 1 sigma and everything above mu plus 2 sigma, or you could just find the complement of the last problem, which is what I'm going to do. And the complement is 0.225. So there's a 22.5% chance that the yogurt in our container will weigh less than 5.98 ounces or above 6.04 ounces. If a container has just been selected from the production line, what's the probability the container weighs less than 6.04 ounces? 6.04 ounces is 2 standard deviations above. So that's mu plus 2 sigma. We're going to look for mu plus 2 sigma. We want less than 6.04. So that's everything to the left of mu plus 2 sigma. Now, there's a lot of things we could add, but we could try to use the symmetry of the graph to help us add less things. For example, everything below mu is 50% or 0.5. So we can just take 0.5 plus the 0.34 and the 0.135. Or you could add everything up, you're going to get the same answer. I'm just saying we know that everything to the left of mu is 0.5. So instead of putting that all in the calculator, we can just say, oh, that's 0.5, and then the other two parts we add with 0.5, and we get 0.975. So there's a 97.5% chance the container weighs less than 6.04 ounces. Our next topic is the standard normal distribution. So here in the graph to the left is the empirical rule, where we've talked about this. Mu is in the middle, and we're adding and subtracting certain numbers of standard deviations. We can switch mu to 0. Instead of having mu in the center, we can put the number 0. And instead of having mu plus 1 sigma, mu plus 2 sigma, we can do 1, 2, 3. And on the left, we can have -1, -2, -3. So what we're doing is rescaling. We're taking the normal distribution and scaling it to something called the standard normal distribution. If we have a random variable that we know is normally distributed, we will often standardize our data by using something called a z-score. Why would we want to standardize? Well, one reason is to make comparisons. Sometimes we want to compare two different normal distributions. For example, the SAT and the ACT. The SAT and the ACT have different means and different standard deviations. And maybe one of your friends took the SAT and another friend took the ACT, and you want to compare how they did, like who performed better on their test. Another example is comparing percentiles for height and weight of children in different age groups. Different age groups have different means and different standard deviations for height and weight. And so you may want to see if they're on track in their height category or if they're on track in their weight category. Z-scores also have special meaning. They're the number of standard deviations above and below the mean. So how do we standardize with z-scores? The z-score of an observation is the number of standard deviations it falls above or below the mean. The formula for finding a z-score is to take your value for x and subtract the mean and divide by sigma. We'll see some examples of this, and we'll also think about it logically, get there a little bit quicker than using this formula. Here's our first example. The distribution of scores for students who took the SAT and the ACT are nearly normal. The SAT, the mean is 1150 with a standard deviation of 200. And let's say the ACT has a mean of 21 and a standard deviation of 6. Suppose Anne scored a 1350 on her SAT and Tom scored a 33 on the ACT. Who performed better? Relate Anne and Tom's scores to the rest of the students who took the exam. How many standard deviations above the mean is Anne's score? So all we have to do is add one standard deviation to the mean to get Anne's score. So her z-score is the number of standard deviations above the mean. It is 1. While Tom's score, if you take 21 and add 6, you get 27, and then you add 6 again, you get 33. So Anne's z-score is 1, while Tom's z-score is 2. The z-score is the number of standard deviations above the mean. So Tom is 2 standard deviations above the mean, while Anne is 1 standard deviation above the mean. You can use those formulas you can use that formula I just showed you, x minus mu divided by sigma. But for this problem, you can also just logically think about it. You're going to get the same answer. Now, if we look at the empirical rule, the standard normal distribution where mu is equal to 0 at the top here, we have this graph. Anne is at 1. And notice that below 1, well, where 0 is, that's 50%. And if we add 34, that's 84%. So 84% of people did worse than Anne, while 16% of people did better than Anne. So Anne is on the 84th percentile. She performed better than 84% of the people taking the SAT. While Tom, his Z-score is 2. And so he actually did better. So if we add 13.5 to 84, we get 97.5 or 98%, or about the 98th percentile. He performed better than about 97.5% of students who took the ACT. So suppose Paul took the SAT and his Z-score was negative 0.5. What was his actual SAT score? Negative 0.5. That means he's half a standard deviation below. If it's negative, it means we're below the mean. If it's positive, it means we're above the mean. Because it's negative 0.5, we're going to half the standard deviation and subtract it from the mean. That means he got a 1050. Now let's also use the z-score formula. The z-score formula was x minus mu divided by sigma. And this time we're trying to find x, the SAT score. We know that the z-score is negative 0.5. So you can solve for x by multiplying both sides by 200. You'll get a negative 100 is x minus 1150. And then just move 1150 to the other side and you get 1050. Just like how we did it logically, you can solve and find his SAT score using this formula. Suppose Anne plans to take the SAT. What's the probability that Anne scores between 1150 and 1550? We've actually done this problem before. We let X be her SAT score, and we want the probability X is between 1150 and 1550. $11.50 is the mean, $15.50 is 2 standard deviations above the mean, and we ended up getting 0.475. The only thing that I wanted to do differently about this with this problem is to think about it in terms of z-scores. So we could think of this as the probability x is between 1150 and 1550, or we could think of it as the probability z is between 0 and 2. Both of them will give us the same answer, which is 0.475. Suppose Barbara plans to take the ACT. What's the probability that Barbara will score above a 27? Let's see if we can write this using z-scores. So if I take 6 and add it to 21, I get 27. So I want the probability z is greater than 27 because she wants to get a score above a 27. So I'm going to look over here for where z is equal to 1. The probability that she makes less than 1 we've done in the past, that's 84% or 0.84. So all we need to do is find 1 minus 0.84, and we get 0.16. Suppose April scored a 1250 on the SAT. What is April's z-score and what is her percentile? In other words, of all the people who took the SAT, what percentage of people scored below 1250? Well, because she's between the 0 and the 1, her z-score is between 0 and 1, she's somewhere between 50% of people performing worse than her and 84% of people performing worse than her, because at 0, 50% of people, that's the 50th percentile, 50% of people performed worse than her. And if her z-score was 1, 84% would have performed worse than her. Now, we cannot just half that because this is not a uniform distribution. All of the columns in the histogram are not the same level, so we can't half it. The columns to the right of 0.5 are actually shorter than the columns to the left of 0.5. So what we could do, there's a few options. The first option is calculus. Calculus tells us how to find the area under the curve. And so we would need a formula for the curve. And this is not something we have to do. I just want to mention it. In calculus, you could find the equation of the curve, and then you could integrate. So that's one option. Another option is using something called a z-table. I'll show you how to use that in the next video, and I'll also explain how to use statistical software to figure out her percentile, or the percentage of people who performed worse than her. So to summarize, we can only use the empirical rule when we are working with z-scores that are 1, 2, 3, 0, -1, -2, -3. If we get something that's like a half a z-score or 0.6 or 3.25, we have to use something else other than the empirical rule to estimate probabilities. We will cover that in the next video.